Let's see. Nope. Got an email. Oh no, Tim, it just lasted a bit longer than I thought. Good morning, Tim. Hey, Isabel. Hey, Vicky. I just gotta boil some water for some tea. I'll be right back. Hey, hey, Sumai. Hey, Justin. Hey, Jennifer. It's good to see you. That's everyone, right? Hey, Josephine. Thank you for the exclamation point. Amazing. Hey, Alexi. Good morning. Esther, please don't be mad. Hello. Good morning. Hi, Allison. Ooh. Ooh. Tina. Alanis, you okay? What's Tina? Aiden, hello, good morning. What are you singing now, Aiden? Josephine, you're Tina? Aiden, is there anything you're singing right now that you, hey, Alon, Labiba, hello, um, that you like, that you're into, that you want to share with us? Josephine is so not Tina from Bob's Burgers. Are you kidding me? No. Which aria is Aiden? Please tell me. Uh, no, like, for example, if Josephine feels a little bit weird about a situation, who's that by? Il mio bel foco, right? So who's that? So when Josephine feels a little weird about a situation, she'll just like smile, right? And but what Tina will do is she'll just go like, make that really unpleasant. Like, Josephine wouldn't do, right? So I feel like Tina is like infinitely more awkward than Josephine. Um, they're both like a little reserved, but I mean, plenty of people are like that, right? No, it is not. Uh, well, now what does that make you, Alanis? Are you Louise? Can I be Linda? I really like Linda. She's definitely my favorite. I was gonna suggest that, but I was afraid you would take offense to me calling you Jean. But I'm glad we can both agree. I feel like not a lot of people would like to be Jean, but power to you. Okay, so let's go over really quickly some more advanced applications of standing waves, and then we'll be completely ready to kind of talk about like how these are implemented in musical instruments. Okay. So the first thing that we really need to go over is not this. Alanis, you can call me Linda, okay? So, what do we have to remember? That standing waves are caused by reflections. And reflections have, so I want to get into, actually today will only be about reflections. Okay. And we're going to go over a very important classical problem in physics. Okay. Reflection is defined as like a change in direction of the wave. It's like if a wave is going in one direction, it'll be sent in the opposite direction. We know all waves follow the law of reflection, right? Which just means if I have a boundary here, if it enters at this angle, it will exit at that angle as well, right? But I think what something a lot of us have been taking for granted is like what a boundary is. So today we are actually going to define a boundary. What's a boundary? It's any place where I shift from one medium to another, right? It's the dividing line between one medium to another. So what's an example? Here, this is a boundary, right? Because my material is air, and then there's a shift into paper, right? In terms of waves, like a really famous type of boundary is like the water-air boundary, right? So this is the divide between any two different materials. All right, so if I have water and air, this is a boundary. So what does that mean? That means if I send a sound wave this way, right? If I point a speaker this way, someone here could hear it because the sound wave would reflect in here. And same thing happens underwater, okay? Like if there's a dolphin here, right? And they send a sound wave this way, A dolphin here could hear it. Right? So because sound reflects at anytime I have a boundary, I have reflection. Okay. So here's a really classic problem, right? This is something every physics student should know once they've taken their junior year physics class, right? So this is one of our nuggets of essential knowledge, okay? It's quite floral, yet vegetative. Okay. What, Tim? What's so whoa? Whoa. Let me create a very unconventional boundary, right? Remember, all I've done to define a boundary is the divide between two different materials. So let's say I have a very light string and I tie it to a very heavy string, okay? Something very dense, okay? Why is this significant? Because my wave is fast here and it's slow here, right? This is a really slow medium through which a wave would travel. And then the wave would travel really quickly, okay? Yeah. All right, so here's the problem, right? I'm gonna send some waves this way, right? And they're traveling this way. And I know the formula. What is that V? I don't know, but if I knew how quickly I was doing this and the frequency here, boom. And then these waves then enter, right? They enter the new medium. What is going to change? I know my velocity will actually decrease, right? So no longer are we dealing with a problem where velocity is constant and, oh, if lambda goes up, then frequency goes down, right? Like, I don't really know that anymore. Because the sound waves travel through the string. Here's the cool thing. At any boundary, part of the wave goes through and part of the wave gets reflected. So what's going to happen at this boundary is that some of these waves will be reflected. Like a very small part of it will get reflected, right? But the majority of it will go into this thick rope, right? So there's always a transmission coefficient, which is the percentage of the wave that passes through, and a reflection coefficient, which is the amount of the percentage of the wave or the energy that gets reflected. And the percentage is going to depend on like the boundary itself, how that's constructed, the difference of speed in the materials themselves, right? So, but right now so even though I preface this by talking about reflection, and you should know some of the wave passes by, what I really am more curious about is the wave that passes through, right? So when the wave enters the thicker string, like there is some part that will get reflected, and that creates a really small standing wave in this rope. I'm more curious about what happens in this rope. When it slows down, velocity will decrease. what happens? Do both frequency and lambda decrease? Does frequency stay the same and lambda decrease? Does lambda stay the same and frequency decrease? Does lambda decrease and frequency increase, but lambda decreases more than frequency? Does frequency decrease and lambda increase, but frequency decreases more? Because eventually, like, the velocity needs to slow down. What happens? You will know. The answer is frequency is constant and lambda decreases. I want you to think about why and type up an explanation. Don't enter it in the chat yet, but I want you to explain why would you expect the frequency of the wave to be constant. You don't have to explain why wavelength decreases. That follows from frequent. So if you can explain why frequency is constant, you basically also explain why lambda decreases, right? Because why? If I know velocity decreases and frequency is constant, then that necessitates that the wavelength has to decrease, right? So all you have to do is explain why frequency is constant. Type it into the chat. Don't enter it. I want you guys to enter it all at once, and I'll be back in a minute. Okay, I just need to boil some more water. So while everyone types up that answer, I hope I answered your question. The sound does bounce off, but part of the sound also enters the string. Is it half and half? No. I would say a majority of the sound is reflected, which is why it's really faint when you listen to it. Right? Well, I mean, it's kind of loud, but it's a lot quieter than if someone were to talk directly into your ear, right? All right, I want everyone to put in their answers in the chat. What are we dealing with right now? Why do I expect frequency to be constant? I'm very curious to see your responses. Don't be afraid of being wrong. Everyone's wrong, okay? I just want to see like what we're thinking so far. Because there's a specific amount of waves being passed through each second. Yeah, like, so what Josephine is just basically, frequency is constant because there aren't any more waves being made, right? So here is my analogy, okay? Raise your hand, right? Say yes in the chat if this is something that you have like a really pretty solid idea of, like you're 80% there and it makes a lot of sense why frequency is constant, but it's super hard to explain in words. Type in yes in the chat if that's the case. If that's the case for you. Like, you kind of get it, but it's just super hard to explain in words. You're not alone. I count myself among you. Wait, it's just Justin? So that means everybody else just has no idea. That's what I'm assuming then. Which is fine too. This means we're going to have to go over this in a bit more detail than I thought. All right, then. To that, here is my analogy and my explanation. Let's say I have a hallway, and here I put like some glue, all right? So it's really slow, okay? Or no, I'll make this water, right? And this is land. And here I release a rat every 2 seconds, right? Right? I release a rat every 2 seconds. So what's my frequency? My frequency is 0.5 hertz, right? It's half a rat a second because the period is 2 seconds, right? Now, someone here, what do they observe? They observe, oh, I see a rat every 2 seconds. What does someone here see? They see a rat that passes by every 2 seconds. What does someone here see? A rat every 2 seconds, right? So what I'm saying is a rat enters the water every 2 seconds. And it's the exact same frequency at which a rat enters the land from my cage every 2 seconds. So the frequencies are identical. And because it's much slower, the rats slow down and they become much closer together, right? Because, like now the frequency is the same, but they're a lot slower, so this rat travels barely any distance by the time this rat catches up to it, right? And that's why the wavelength, and then like every one rat looks at the water and nopes out every now and then. We're like, nope, right? So that's why the frequency, so hopefully this analogy kind of helps explain like this, like why this is constant, why this decreases, right? That's all I will leave you with today. No practice today either. Take it easy. I know there's a lot going on. If you guys feel a little overwhelmed or anything, please don't hesitate to reach out. Email me, say like, Mr. So, like I don't feel good. I haven't done like the past 7 assignments. I have no idea like how I'm gonna like do everything. It's okay. Just let me know, all right, and stuff like that. We'll work through it. If you're not feeling so hot, like please let me know. So I'm just like gonna not give work for the rest of the week until Monday. So if you are one of those students who are a little behind on work, please take this time to catch up, or at least study for your APs if that's what you really want to do, even though I think those exams are lame. Yep. Have a great day.